Hi everyone. So this lesson is lesson 251 that it should say on the top of your sheet of paper. We're going to talk about analyzing exponential functions. You're going to see that it's pretty similar to what we did back in Unit 1 with exponential functions. Okay. So this is what the top of your notes looks like. So we'll just kind of go through the warm-up together here. It says simplify for number 1 and number 2. You can use rules of exponents here. Because you have x raised to the second and raised to the fifth, you would multiply those exponents and you would get x to the 10th power. So just to review, if you had something like x squared times x to the fourth, that's when you add your exponents, making it x to the sixth. So you may want to write that down. Whereas when you take one and raise it to another, notice that there's a parentheses in between them. That's why you're multiplying. Okay, we're going to do the same thing over here. This 2 has to be distributed to the 3, to the x, and to the y. So 3 squared gives us 9. If we have x raised to the fourth and then we raise it to the second, we multiply those, which gives us 8. Y raised to the third, raised to the second, we multiply those, and we get y to the sixth. Okay. The population of a small town in 2001 was 2,800 people. And then in 2005, it was 2,050. So you can see that the population is decreasing as time goes on. Find the rate of the population from 2001 to 2005. Okay, so let's start off with an equation. Exponential functions are y equals a times b to the x power. Okay, so 2001 happened first, so that's our initial. And 2005 happened second, so that's our ending. Okay, so in 2001, our initial value is 2,800. So we're going to say 2,800 people times a rate that we don't know, we're going to figure out. Our time, our x, would be how many years from 2001 to 2005, which is 4. Okay, and that's going to be equal to our ending population, which was 2,050. Okay, so if it's 2,800 times b raised to the fourth, the first thing that I have to do is divide by 2,800. And if you guys haven't already, forgot to remind you, you're going to need your calculator, so take your calculator out. You're going to want to do this with me. Alright, so put 2050 divided by 2,800. Okay, we're going to round at the end, but right now we're going to keep that number in our calculator. So I'm going to write 0.73 equals b to the fourth power. If you remember back from Unit 1, if I want to undo raising to the fourth, I raise to the reciprocal power. So I raise to the 1/4. And this is going to tell me that my rate is about... I'm going to use that exact answer, so I'm going to raise that to the 1/4. Okay, and it gives me that. If you remember back in Unit 1, we used 4 decimal places. So I'm going to say 0.9250. Okay, and that would be our rate. Normally we interpret what that means, but that's what the next question is going to ask anyways. It says interpret the rate in the context of the problem. So this means that it percentage-wise is 92.50%. Which is a decrease. Remember, decreases are always how much do we fall from 100%. So that would be a decrease of 7.5%. You could also take your calculator and do 100 minus 92.5. And you're looking at 7.5 or 7.5 is. So you want all of that. You want to interpret it as 92.5% and then say which is a decrease of 7.5%. And that's what we're going to kind of talk about a lot today. Okay, so now we're going to put some formal notes to this in case you've forgotten some things. So first, let's talk about what each of these values mean. This is the end amount. Opposite of that, A is your initial amount. B is your rate. That's what we just solved for in the last problem. and then x is your time. Okay? Alright, so the first part is going to talk about the difference between exponential growth and decay. Remember that growth must be above 100%, so must be greater than 100%, and then decay must be less than 100%. Okay, so I have some examples for you. We want to determine if it's growth or decay. So really the A value does not matter, neither does the time. I just want to look right here at this. That is 112%, which is above 100%, so that would be growth. This one is 67%, which is less than 100%, so that would be decay. This one is 103%, which is greater than 100%, so that would be growth. This one is 81%, which is less than 100%, so that would be decay. And this one is 95%, which is close to 100, but still less, so also decay. Okay, so really you just want to identify what the percentage is. Above 100 or below 100 is going to tell you growth versus decay. Got it. Start one in context. A school tracks the total number of students enrolled each year. The school uses the change in the total number of students to estimate how many students have been enrolled in the school each year since 2000. So each year since the year 2000. If t is the number of years after 2000, so notice we're talking that's our milestone, that's our starting, the total number of students f of t can be estimated using this function. Okay, so I would do a couple things first. I would I try to understand what this equation means. So notice that the 250 is your A value, so that's your initial amount. And the 0.98 means that that's 98%, which means it's a decrease or a decay. You could say either or. It's a decay of 2%. Okay, so that kind of gives us an idea going into answering questions. The first part says, what is the yearly rate of change of the function? So that is our 98%. That means that we're retaining, I'll write that down, that we are retaining 98% each year. Because we're only retaining 98%, that means we're losing 2%. So how does the rate of change relate the change of the dependent quantity? This is where we just want to say decay of 2%. So the function has a rate of 98%, but in terms of what's happening every year, there's a decay or loss of 2% of students. Is the dependent quantity growing or decaying? We just said it was decaying. Okay, and then lastly, what is the number of students enrolled in 2015? Well, this started in 2000, in the year 2000, so that means our t would be 15 years. So we can just substitute this in. So we can say f of 15 equals the 250 that we started with times the 98%, and then we can raise it to the 15th power. And going in, we should know that we're going to end up with something less than 250. So 0.98. Oops. And you should be doing this on your calculator too. Raise to the 15th. So we end up that we get that x is about, if I rounded 2 decimal places, I have 184.64. However, this is talking about people, so it doesn't make sense to have a portion of a person. So we'll use our rounding rules. We'll round this up. So that means that there is about 185 students. So in 15 years, there will be about 185 students if it continues at this rate. All right. Go ahead and flip over. Okay, so now we're going to talk about how how exponential functions can be a little bit deceiving. Okay, so think about this. I want you to write down x to the second raised to the 6th power. Okay, we just talked about that on the front. We would multiply those together, and that would be x to the 12th power. Okay, we can break those up. So let's say I started with something like x to the 14th power I could say that that's the same thing as x raised to the second raised to the seventh. Okay? That's what I'm going to use here. So, and I wrote it out here for you. It says y equals 0.83 raised to the 3x power. And then notice here it's broken up. This is raised to the third and then raised to the x power. Because if I have 0.83 raised to the 3x, I don't know what x is, so I cannot put this in my calculator. However, if I break up the 3 and the x, I can put this into my calculator and simplify it a little bit further. Okay, so if I put into my calculator 0.83 and I raised it to the third power, notice that's where this is coming from, and then raised to the x power. So it looks like when we started this problem, it looks like there was an 83% rate, but really there's a 57% rate. So it's deceiving. That's what we're trying to avoid. We don't want to look at this and think that there's an 83% rate when there's actually a 57% rate. Okay? So for instance, I would look at this and I would think that there's a growth of 9%. So I look at this and I think, okay, it looks like a growth of 9%. However, I can break this up and I can actually say this is 1.09 raised to the 7th raised to the x, and then I can put that in my calculator. Okay, and I'm going to say that this is 1 point, and I'm going to use 4 decimal places, 8280. So when we use percentages, we always want to use 4. Okay, which means that this is not actually a growth of 9%, it's a growth of 82.8%, which is insanely more. Okay, and that's what we're trying to get at. So simplify the following to determine the yearly rate. So that would be my yearly rate, a growth of 82.8. So not 9, even though it looked like that. Okay? Alright. In the next one, again, we start the next one and we see that there's a 0.99, and we think that the yearly rate is a decrease. So just, you don't need to write this off to the side always, but I would for notes. It looks like there's a decrease or a decay. Those are interchangeable words. So it looks like there's a decrease or a decay of 1%. But if we actually simplify this, we can say 1.06 times 0.99 raised to the 10th raised to the x. So that's the same thing. So in my calculator, I can say 0.99 raised to the 10th power, and that becomes then 1.06 times 0.9044 raised to the x. I can't simplify this anymore. Do not multiply those two numbers together. Then you're doing multiplication before an exponent. Okay? Okay, but I can see that the decrease of 1%, it's definitely not a decrease of 1%. It's now a, let's see, I'm going to write this out for you to see. It's 90.44%. Okay, so I have to subtract that from 100. So I'm going to do 100 minus 90.44. Okay, and it's actually a, again, decay or decrease, either or. Decay has less letters. So it's a decay of 9.56%. Okay, it started looking like it was 1%, but it really is 9.56. So the whole point is it's deceiving. Okay? Okay, moving on. A bank offers a savings account with interest that is compounded monthly. Jackson opened a savings account with $500. If T is the time in years the account has been opened, the balance in his account F of T is represented by F of T equals, box this, 500 times 1.004 raised to the 12th T. What is the estimated yearly exponential growth rate? So we start by thinking that it's this 0.004 growth, but because of that 12, we're going to want to rewrite this. So I'm going to write 500 times 1.004 raised to the 12th raised to the t, so that I can see in my calculator I can put 1.004 raised to the 12th. Okay, and that gives me 500 times 1.0491. Be careful with your rounding. Raised to the t. Okay, so what is the estimated yearly exponential growth rate? So this, as a percent, is 104, right, the first two decimal places, and then 0.91%. So the exponential growth rate is, I'm going to say growth of 4.91%, which is much better than it originally looked, because it looked like it was less than 1%. So growth of 4.91%. Okay, so same thing we did in the last two problems, just a word problem. Next one. A number of bacteria f of t at any time t in hours can be estimated using the function f of t equals 3,000 times 1.24 times raised to the t. Okay, what is the initial size of the bacteria colony? So 3,000 bacteria, right? That's your initial. Okay, so that answers the first part. Is the bacteria population exponential, growing or decaying? This is over 100%. That represents 124%. Sometimes writing that out helps. That means that there is a growth of 24%. So actually no algebra or anything, calculator that we had to use, just had to basically dissect the equation. Alright, last one. Kristen is buying a new car and trying to decide between two models. Both cars are the same price today, but the value of each car will change over time. According to Kristen's research, the first car will have a value of $V after T years, and the value is modeled by V equals 22,000 times 0.9 raised to the 2t. The second car will have a value of $V after 2 years and is represented by the equation V equals 22,000 times 0.86 raised to the t. Kristen wants to buy the car that will have a higher value in the future. Okay, so that makes sense. She wants to make sure that in 5, 10, 15 years, whatever car she bought is worth more than the other one. Okay, so she wants the one that's going to maintain the most value. What is the value of both cars today, and which car should Kristen buy? Okay, so first of all, I'm just going to rewrite these equations so that we see them. So here's my first one. And I'm going to rewrite this so that it's raised to the 2 times t. And then over here, I'm going to have V equals 22,000 times 0.86 raised to the t. So what is the value of both cars today? Both cars are worth, how do I spell worth? $22,000. Worth, we should have dollars. $22,000. So that's the initial value of both. Okay, so that would be the answer to the first question. Which car should she buy? Well, at first, it looks like this one is going to maintain more of its value because that one's only decreasing by 10% and that one's decreasing by 14%. However, we need to simplify that first. So this equation is actually going to become V equals 22,000 times, I'm going to use my calculator to say 0.9 raised to the second power. It becomes 0.81. So 0.81 raised to the t. So that means that this one is 81%, which is decay of 19%. This one over here is 86%, which is decay of 14%. Okay, and here's another way to think about this. If this one's 81% and decay of 19%, that means that it retains 81% of its value every year. This one retains 86% of its value every year. Okay, so in terms of which one is going to be worth more money in the end, it's going to be retains 81%, retains 86%. So it's going to be this card because it retains more percent, or it has less decay. This one only decays 14% compared to this one decaying 19%. Okay, so I'm going to say the second car. So which car should she buy? The second one, if she wants it to be worth more money in the end. Second car. Okay, so you should kind of see a theme here. The theme is that it looks deceiving. At first, this looked like a decay of 10% compared to a decay of 14%. But by simplifying this using rules of exponents, we can actually see its true value. Okay? Your homework's going to be worksheet number 9. Okay, it's going to look like this. Pretty much the same thing. Alright, over the weekend, please make sure that you guys are caught up on all of your homework, especially the calculator stuff. Monday, we're going to go through and do, what are we going to do? Monday, we're going to talk about some classwork with exponentials, and then next week's going to be a busy week. We'll have test review, group challenge. Okay, you're also going to get the test review today, so feel free to get started on it over the weekend and get a good head start for next week to make sure that you have some good study time for the test next Friday. All right? All right, great.